Okay, now we'll talk about specific heats. So when it came to solids and liquids, we had defined specific heat as mass times specific heat. Okay, so in this formula tells you how much heat do you need to heat this much amount of the substance by this, to raise the temperature of this much amount of substance by that amount. And this was the specific heat. So when it came to solids and liquids, it's easy to measure the quantity of the substance in mass. Okay, and that's how we define the specific heat. Now, when it comes to a gas, it's a more convenient quantity rather than the mass is how many moles of gas you have. Okay, so what we want to define is a molar specific heat for a gas. So this is called a molar specific heat. Just because it's more convenient to measure how many moles of a gas you have. Now, again, in the molar specific heat, now when you add heat to a gas, it's easier to do the molar specific heat at constant volume. So here are or constant pressure. Okay, so, and okay, so when you add heat at constant volume, this is how much heat you added, CV times delta T. And if you add heat at constant pressure and CP delta T, that's how much heat you've added. And CV is specific heat at constant volume and CP is specific heat at constant pressure. And you will see in a little bit that CP is CV plus R. Okay. So for an ideal gas, specific heat at constant pressure is greater than specific heat at constant volume by R. Okay, by R. So it takes more heat energy to raise the temperature of a gas by a given amount of temperature rather than at constant volume. Okay. And now let me derive CV for you guys. Okay. So let's derive CV. Yeah. Now let's say you have an ideal gas, we have an ideal gas, and each molecule has F degrees of freedom. Okay. So again, let's see, what does that mean, F degrees of freedom? So let's look at a diatomic molecule. Okay. So here are various molecules. So and here is a helium atom. This is noble gas. All this guy can do is it can move in the X, Y, Z or Z direction. So this guy has only 3 degrees of freedom. Now here's a diatomic molecule. This guy can move in X, Y, Z direction, but he can also rotate. He can rotate about this axis or rotate about that axis. So this molecule has 5 degrees of freedom. It turns out that it cannot, well, it can also rotate about the Z axis, except that the energy of the first excited state when it rotates along the Z axis is quite high. So that degree of freedom is never in place, okay? So here's a diatomic molecule with 5 degrees of freedom. Here's a more complex molecule that can rotate about all 3 axes. So, and then it has translational degrees of freedom. So this would have 6 degrees of freedom. All right, so we saw that a molecule can have various degrees of freedom. So generally, when we consider monoatomic gases, that would be 3. For diatomic gases, that's 5. And And for diatomic gases at high temperature, you get vibrational degrees of freedom, and that can increase to 7. But anyway, so that's what that degrees of freedom means. Okay. So the energy of a gas, that gas is N times the number of degrees of freedom, and half kT is the energy contributed by each degree of freedom. And CV is defined as, and by the way, NK is N times R. Okay. The number of molecule times the Boltzmann's constant is the number of moles times the gas constant, equal to, so F by 2 N R2. Okay. CV is defined as 1 over N dE by dt. Okay. And so C, this is equal to 1 over N del by del T of F by 2 N RT. Okay. And so, oops, this is N. So what you end up getting is F by 2 times R. Okay, so what we have is the specific heat of an ideal gas at constant volume is the number of degrees of freedom divided by 2 times R. Okay. So very important relationship. So let's go back to the lecture. Okay, so the slides here. So again, like I said, for gases, it's more convenient to measure the number of moles of the gas, and so we define molar specific heats at constant volume and constant pressure. So molar specific heat at constant pressure is always greater than the one at constant volume. Okay. So here's an ideal gas. These are the isotherms. Isotherms are constant temperature curves, and so this is pressure, volume. So if you were adding heat at constant volume, this is the path you would take. If you were adding heat at constant pressure, this is the path you would take. Now, it takes a certain amount of energy to increase the temperature of the gas by that much. But if you went along this path, you did work as well. And so you need more energy. Along this path, you didn't do any work, and all the energy went into just warming the gas. Okay, so that's why CV is lower than CP. Okay. All right, so the internal energy of a gas is the number of gas molecules. So for an ideal gas, for ideal monoatomic gas, so for an ideal monoatomic gas, all it can have is translational kinetic energy. So N times average kinetic energy. Okay. But this is equal to 3/2 kT. So the internal energy is N times 3/2 kT, which is equal to 3/2 nRT. And CV is defined by that. So it's 3/2 R. So for an ideal monoatomic gas, since it had 3 degrees of freedom, the CV was 3/2 R. But as we saw, for a gas with F degrees of freedom, CV would be F by 2 times R, where F is the number of degrees of freedom. Yeah, so F is the number of degrees of freedom. Okay. So for all monoatomic gases, we should have CV equal to 3/2 R, which is 12.5 joules per mole per Kelvin. And let's see, I should have a table. Oh, okay. Well, so your book has a table, and you'll see that for all the noble gases, it's roughly that. So now we'll consider a molecule with F degrees of freedom. Again, like I said, this guy can have only 3 degrees of freedom. This guy has 5 degrees of freedom. And this guy has 6 degrees of freedom. This is when the vibrational degrees of freedom are not excited. When the vibrational degrees of freedom are in play as well, then this guy will have 7 degrees of freedom. This molecule can vibrate like that. That molecule can vibrate like that. So, that is F degrees of freedom. Each degree of freedom contributes 1/2 kT towards the energy. Okay. So shown are the rotational degrees of freedom for helium, nitrogen, and methane. Okay. So the internal energy is 3 times. So this is again for a monoatomic gas. Okay. So no. So this is for a diatomic gas. So this is the translational degrees of freedom, and this is the 2 rotational degrees of freedom. Again, this rotational degree of freedom and this rotational degree of freedom is inaccessible because the energies, even for the first excited state, are too high. And here are the 2 vibrational degrees of freedom. Okay. So, and also those energies are high, and you don't access those energies, those degrees of freedom, till you raise the temperature of the gas quite a bit. Okay, so this is with 5 degrees of freedom. So CV is 5/2 R. All right, so here is CV plotted for a hydrogen molecule. Okay, so at low temperature, the hydrogen molecule, even the rotational degrees of freedom are not excited. So CV is 3/2 R. At room temperatures, again, the temperature is in Kelvin scale. So at room temperature up to 500 degree Kelvin, the rotational degrees of freedom are excited. So now it has 5 degrees of freedom, and CV is 5/2 R. Okay, and at 10,000 degree Kelvin, around 10,000 degree Kelvin, the vibrational degrees of freedom are excited as well. And so now CV is 7/2 R. Okay, so you can see that CV as a function of temperature is an interesting plot. It tells you how many degrees of freedom are in play for the molecule. Okay. So that's what this is. For hydrogen molecule, separation between the lowest vibrational energy levels is 10 times greater than the average kinetic energy. Okay, so these, to excite the vibrational level, the temperature essentially has to be 10 times greater than this. Okay, so so you want to excite the vibrational levels until the gas is very hot. So the hydrogen molecules on Earth will not vibrate. They'll have rotational degrees of freedom. But hydrogen molecules in the sun's atmosphere, the vibrational degrees of modes have been excited. So the vibrational modes do not come into play at low temperatures, and they do not contribute to the specific heat. Okay. All right, that covers the topics. Okay, again, let me summarize what we've studied. One of the big things about this chapter was, so I'll give you the 2-3 main points. Okay. So one of the big things was relating macroscopic quantities to microscopic quantities. Okay, so here is a macroscopic quantity, the pressure of the gas related to the average kinetic energy per molecule. We got an expression for the kinetic energy. Okay, again, here's a microscopic quantity and here's a macroscopic quantity. Okay, so 3/2 kT, the average kinetic energy per molecule is 3/2 kT. Okay. Underlying this expression is each degree of freedom from a molecule contributes 1/2 kT to the energy of the system. Okay. And so that's the equipartition of energy, and that's extremely important law. Okay. And CV for an ideal gas is F by 2 times R. F is the number of degrees of freedom. And CP, which we didn't prove, we'll do that in the next chapter, is CV plus R. So CP is greater than CV by R. All right, so that covers the topics from this chapter. So what I'll do is I'll stop the recording now and let you guys